This is the fourth talk about basic electronics in neurophysiology. The purpose of this talk is to explain a few concepts about capacitors that are relevant to the neurophysiology board examination. These concepts relate to two issues. The first issue is the use of capacitors in the electronic circuits of the EEG machine. Capacitors in the electronic circuit of the EEG machine are used coupled with diodes to act as power supply filtering devices and in isolation as temporary power sources. The purpose of a power supply filtering device is to transform alternating current into direct current. The purpose of temporary power source is to supply electricity in the event of a power failure. The second issue about capacitors relevant to neurophysiology boards testing relates to the processing of the EEG signals. Capacitors contribute to the processing of EEG signal by their ability to selectively allow electricity to go through or be blocked based on the frequency of the signal. This attribute, when coupled with resistors, is used to build EEG filters. This talk will be conducted in a question and answer format. The first question is, which of the following is not a component of a capacitor? A. Plates, B. Insulating material, C. Dielectric, D. Solenoid. In this frame, I have represented a capacitor. The yellow cylinders represent wires. The wires are in contact with two rectangles. The rectangles represent the conductive plates of the capacitor. The rectangles are separated by an insulating material. This material is called dielectric. So the answer to this question is D. Next question. The symbols for a capacitor is, as you can see there, A, B, C, and D. In this frame, I would introduce all the symbols matched with their names. First, you can see the resistor that, as you know, in the United States is represented by a zigzag line. Second, an amplifier. Third, a capacitor. Notice that one way of representing a capacitor is by two parallel lines with one of them being curved, and the other way is to represent a capacitor by two straight lines of equal length. And the last symbol in this frame is the battery. The battery is usually represented by two lines, one longer than the other, or by a repetition of the two unequal lines. So the answer to this question is C. Next question. The charging and discharging of a capacitor occurs because of movement of electrons across the capacitor's dielectric. A. True, B. False. Capacitors have an insulating material. Electrons do not cross the insulating material. They excite the opposite plate by their negative electrical field. This book that I am pointing with the arrow is a funny book about electrons. I think it was in it that I first read the analogy between electrical field and the sound of music. I have adopted the analogy. So I think about conductive plates of a capacitor as two parking lots separated by a river. The music from party goers with radios in one parking lot can make the people in the other parking lot across the river dance, despite themselves having no radio. This is so because the sound of the music travels through the air. So the answer to this question is false. Next question. Capacitors convert voltage into heat. A, true. B, false. As you remember from the prior talk, voltage is transformed into heat as current flow through a resistor. In this frame, the running boy with the fire in his backpack represents a volt-carrying electron. After going through the resistor, the boy is just an electron going around a nucleus with no volt. The white lines from the resistor indicate dissipation of heat. We can think of a capacitor as a drawer where volts are kept. So the answer to this question is false. Next question. In the analogy between electricity and water, a gallon of water should be considered equivalent to A, an ampere, B, a volt, C, a coulomb, D, none of the above. You can see in this frame two buckets. One bucket has 1 gallon of water. The other bucket has 1 coulomb of charges. The gallon of water has, let's say, 128 to the 23rd power of 10 molecules of water. The coulomb of charges has 6.24 to the 18th power of 10 electrons. So the answer to this question is C. Next question. Which of the following is not a definition of capacitance? A, the capacity of a capacitor. B, the ability to store charges easily. C, the charge per unit potential. D, the constant charge to voltage ratio. Capacitance has been defined in different ways in different books. In Eversole, capacitance is defined as the amount of charges that a particular device can store for a given potential difference. In electrodiagnostic medicine, it has been defined as the ability to store charges easily. In Jasper, it has been defined as the charge per unit potential, and in Kimura as the constant charge to voltage ratio. All these definitions have one thing in common. They include the charge related to the voltage. So the answer to this question is A. The fact that the capacitance relates to potential must be expressed in the definition of capacitance. Next question. What is a farad? A. Joules per amps. B. The unit of resistance. C. Coulombs per volt. D. None of the above. A joule can be defined as the heat that will dissipate when current of 1 amp flows through a 1 ohm resistor for a period of 1 second. Another definition of a joule is the heat that will dissipate by 1 volt of electricity while going through a 1 ohm resistor. 1 farad can be defined as the capacitance of a capacitor in which 1 coulomb of charge causes a potential difference of 1 volt. Or, more often, it is defined as the capacity of a capacitor to store 1 coulomb for every 1 volt. Whichever way you slice it, the definition of farad has to have coulombs and volts. So the answer to this question is C. Next question. How large would a 1 farad parallel plate capacitor with 1 millimeter air dielectric be? A. About 1 inch square. B. About 1 centimeter square. C. About 10 kilometers square. D. About 100 centimeters square. The farad is a very large unit. Kimura gives an example by saying that the size of the plates separated by 1 millimeter air dielectric would have to be 10.5 square kilometers to hold 1 farad. Hence, the units commonly used for dealing with capacitors are much smaller than a farad. Usually, we talk about microfarad, nanofarad, or picofarad. To give you an idea about the value of a farad, just think that 1 square centimeter of cell membrane has a capacitance of 1 microfarad. So the answer to this question is C, about 10 kilometers square. Next question. Which of the following is not a function of a capacitor? A. Store voltage. B. Resist the storage of voltage. C. Discharge voltage. D. Convert voltage to magnetism. As you remember, voltage is transformed into heat as current flow through a resistor. Voltage is stored in a capacitor. In an inductor, voltage is transformed into magnetism. So the answer to this question is D. Next question. The formula C equals Q divided by V refers to the amount of charge a capacitor can hold for a given amount of voltage applied. A. True. B. False. The formula just expressed in this question can be placed in a triangle for manipulation, as I have done in this frame. This formula can be read as follows. Capacitance measured in Farad is equal to the charge in the capacitor measured in coulombs divided by the volts in the capacitor. It is important to understand that when we talk about volts in this formula, we refer to the volts in the capacitor and not in the battery. They are not always the same value, at least they are not the same value all the time. I will show you. In this frame, I have represented a capacitor not connected to a power source and a battery. At this time, the battery has a potential difference of 10 volts between the cathode and the anode. No potential difference is present between the upper and the lower plate of the capacitor. I have labeled this as time zero. Now the capacitor is connected to the power source. Electrons start flowing from the anode of the battery to the lower plate of the capacitor. As the electrons start to accumulate in the lower plate, they trigger changes in the upper plate. The changes can be described as attracting positive charges to or repelling negative charges from the upper plate. The consequence of this reaction, regardless of how we describe it, will be the separation of charges of different polarity, negative in the lower plate and positive in the upper plate. The separation of charges will generate volts. Initially, the electrons do not have any trouble getting into the lower plate of the capacitor. Neither do the movement of charges have any problems leaving the upper plate. So the number of negative charges in the lower plate and positive charges in the upper plate increases very rapidly. I have expressed this fact, the fast movement of charges, in this frame by indicating that 7 volts have been stored in the capacitor in 1 second time span. Then, as time goes on and more electrons gets in the lower plate becomes more crowded and it becomes harder for other electrons to get in. This is translated by an increased expenditure of energy per electron that gets in the lower plate and by slowing down the current traveling through the capacitor. I have indicated this in this frame by showing that only 2 volts have been added to the capacitor in a 2-second time span. Finally, as indicated in this frame, it has taken almost 3 seconds to add 1 more volt. So the answer to this question is true, A. Next question. The factors subject to manipulation in the formula C equals Q divided by B are A. Volts and capacitance, B. Capacitance and coulombs, D. Volts and coulomb, D. Volts, capacitance and coulomb. In this equation, which we previously described, 2 factors can be directly manipulated: voltage and capacitance. Since, as you can suspect, the relation between these 3 factors is 1, when attaching 1 volt to a capacitor of 1 farad, 1 coulomb of charges will accumulate in the capacitor before current stops. If we increase the volts to 2 and keep the size of the capacitor to 1 farad, then 2 coulombs will accumulate in the capacitor. This will occur as long as the capacitor can take the voltage and does not burn. If you at this point change the capacitor to a capacitor with a capacitance of half a farad, then only 1 coulomb will accumulate. The reality is a bit more complicated because capacitors are also rated by the voltage they can withstand. But we're going to leave this subject at this point because of the scope of this talk and my limited knowledge of the subject. So the answer to this question is A, volts and capacitance. Next question. The formula Q equal to C times V can be expressed as the charge stored in a capacitor is the product of its capacitance and the voltage applied to it. A, true, B, false. Using the magic triangle we have used so often, we can define capacitance. The capacitance of a capacitor is obtained by dividing the number of coulombs by the volts. We can permutate this formula by changing the emphasis to charges, so we can say the number of coulombs stored in a capacitor is the product of its capacitance and the voltage applied to it. Or we can change the emphasis to voltage and say the voltage across a capacitor is obtained by dividing the number of coulombs by the capacitance. So the answer to this question is true. Next question. More volts are required to put coulombs in the conductive plate when current starts than when current is flowing for a while. A, true, B, false. I like to answer this question by using the analogy of a person trying to put socks in the drawer. As more and more socks are placed in the drawer, you progressively need more and more force and more time to fit each of them into the drawer. I show you what I mean in this next few frames. The force that takes to put the first pair of socks in a drawer is very little. That is because the drawer is empty and there is lots of room in it. Let's say it takes 1 unit of force and time-wise 1/10 of a second to put the first pair of socks in the drawer. Putting the second pair of socks in the drawer takes a little more force and a little more time, because when we put the first socks, we decrease the available volume in the drawer. So to put the second pair of socks takes just a little more force and more time than it took to put the first pair of socks. Because since 1 pair of socks is already in there, there is less room in the drawer for the second pair. So let's say it takes 2 units of force and 8/10 of a second to put the second pair. To put the third pair of socks in the draw, it takes even more force and more time. Not for the initial move, but to make it fit in the draw that is now fuller. So let's say that the third pair of socks will take 3 units of force and 1 1/10 of a second to be introduced in the draw. Next pair of socks will take even more force and more time. Let's say 4 units of force in 3 seconds. And this will go on and on with each pair of socks that we try to put in. More and more force and time will have to be expended doing so. Hence, if you establish an analogy between the draw and a capacitor and units of force and volts, you can come up with two conclusions. The more volts in the capacitor, the more force it takes for charges to accumulate in the capacitor. And second conclusion is that the more volts in the capacitor, the more time it takes for charges to be accumulated in the capacitor. So the answer to this question is false. Next question. Time is a factor in the charging and discharging of a capacitor. A, true; B, false. This frame indicates that time is a factor in charging and discharging a capacitor. Exposure to changing voltage, in this case increasing voltage, will ultimately fill a capacitor. So the answer to this question is true. Next question. Which of the following is not a definition of capacitance? A capacity of a capacitor, the ability to store charges easily. C, the charges per unit potential. D, the constant charge to voltage ratio. This question is a repeat, but I included it twice to expand on the definition of capacitance by using the draw pair of socks analogy. Capacitance, as you recall, is defined by different books in different ways. Ebersol defines it as the amount of charge that a particular device can store for a given potential difference. In electrodiagnostic medicine, it is defined as the ability to store charges easily. In Jasper, is defined as the charge per unit potential, and in Kimura as the constant charge to voltage ratio. What is common among these definitions is that capacitance is more than the number of pairs of socks that can fit in a draw. It is the relation between the pairs of socks put in a draw and the unit of force used to put them there. So we can say that a farad is the average of force needed to put each pair of socks in the draw. In this example that we have just looked at, 4 pairs of socks were put in the draw using 10 units of force. So the Farad equivalent would represent that for each pair of socks, 2.5 units of force was spent. So the answer to this question, as you know, is A. Next question. When will more charges per unit of time be deposited? When the voltage between the plate is A high, B low, C medium, D very high. If we could measure the voltage of a capacitor in the instant the battery is connected to it, but before electrons start to flow, we would find the voltage in the capacitor to be zero. By the time the volt between the lower and the upper plate is 4 volts, about 75% of the total amount of electrons will have gone into the lower plate. During the time the other 6 volts go in, only 25% of the coulombs are stored in the capacitor. This relation among current, time, and volt can be remembered by the mnemotechnic rule ICE. Current, represented by the letter I, is the first letter in this word. C stands for in a capacitor, and E stands for electromotive force. The order of the letters dictate what occurs first. So we can say that current in a capacitor increases before electromotive force. So the answer to this question is B. Next question. Which of the following factors is inversely proportional to the capacitance of a capacitor? A. The area of overlapping conductive plates, the dielectric current, the distance between conductive plates, D. None of the above. This formula reveals the relation between capacitance and other relevant factors. It can be expressed as capacitance is directly proportional to the relative permeability of the insulating material to the electrical field. An electric constant, which has the value that you see indicated here, and the area of the plates. But at the same time, it is inversely proportional to the distance between the plates. The relation between area of the plates and distance can be easily visualized, as I will show you in the next few frames. If a capacitor with a plate of an even area is connected to a 2-volt battery and holds 1 coulomb of charges, if the size of the plate is double while keeping all other factors the same, the plate will hold 2 coulombs instead of 1. Now if we go back to the original example and the plates are moved further apart from each other while keeping all other factors the same, the capacitance will decrease. The decrease in capacitance will translate in the holding of less coulombs. So the answer to this question is C. Next question. The formula I equals C times dV divided by dt refers to the rate current moves into a plate of a capacitor and to the rate current is displaced from the other plate of the capacitor. A, true, B, false. The implication of the factor pointed by the arrow in this formula is that the more voltage changes that occurred in the least amount of time, the more current goes through the capacitor. And the higher the capacitance, the higher the current. This occurs regardless if the capacitor is charging or discharging. So the answer to this question is A. The next question is: capacitance voltage is inversely proportional to the capacitance and directly proportional to the total amount of charge that has gone into the plates. A, true, B, false. The confusing point in this formula is the elongated S that stands for integral. I found it easy to understand this formula by thinking about the figures I'm about to show you than by looking at the formula itself. All factors being equal, the larger the capacitor, that is the area of the capacitor conductive plates, the less voltage it will store for a fixed amount of current. Notice that on the other side, the smaller capacitor has a higher voltage. This formula makes sense from a mathematical point of view if we look at the permutation derived from the capacitance equation presented in this frame. This formula dictates that voltage is inversely related to capacitance. In the next frame, I will show you where this equation came from. Take the time to read it. I do not think that the fact that they use a resistor capacitor circuit instead of a pure capacitance circuit makes a difference to the functioning of the capacitor. So the answer to this question is true. Next question. The formula X with a small c is equal to 1 divided by parenthesis 2 pi f c close parenthesis refers to the frequency dependent resistance, usually called reactance of a capacitor. A, true, B, false. This formula reads: reactance capacitance is inversely proportional to the cycles of alternating current. I will explain this term a little better. If you recall, when talking about the generation of alternating current, I told you that the equipment creating alternating current do so by rotation. In this example, by the wire rotating around the magnetic field. This circular motion creates a sine wave with components above and below the midline. This sine wave can be measured in cycles. The whole turn of the circle corresponds to one cycle, or it can be measured in degrees. The whole turn is called 360 degrees, or it can be measured in radians. And 2 pi represents the whole circular motion. Pi represents twice the ratio of the circumference of a circle to the diameter of the same circle. To put it in numerical terms, 2 times 3.14. So, going back to the formula, after the 2 pi, we have the letter F. The letter F stands for frequency of the sine wave and is given in hertz. Finally, we have the letter C. The letter C stands for capacitance. I have introduced in this frame the formula we previously discussed regarding capacitance. I have done so to remind us of the relation between area and distance of the plate and the influence that they have on this formula. The formula that we have just discussed, that is the formula related to capacitance reactance, is the most frequently used formula to express this term. But at times you may see a different formula expressing capacitance reactance. I will explain it to you in the following frame, so if you encounter during your readings on the subject, you do not get confused. The formula I will show you in the next frame substitute the letters in yellow for a different term. This term is indicated by the lowercase Greek letter omega, which indicates radians per second and is used to describe angular velocity. Regardless of the equation used, it is important to remember the relation between frequency and reactance. Capacitance reactance is inversely related to frequency of current. That is, the higher the frequency of the current, the less the capacitance reactance will be, to the point that very high frequencies will go unimpeded by the appropriate capacitor, whereas direct current may be completely blocked. In this situation, the capacitor will behave when dealing with direct current as a circuit breaker, having infinite light resistance. So the answer to this question is true. Next question. Capacitance reactance is the consequence of the repulsion of equal charges in the plates. A true, B false. These frames show a capacitor. The charges in each plate are equal. Once connected to a battery, electrons from the anode of the battery will flow to the lower plate, connecting it to the battery. This will cause an accumulation of negative charges in the lower plate, and they will attract positive charges to the upper plate, thus displacing negative charges away from the upper plate. The accumulation of negative charges in the lower plate will continue until the negative charges in the lower plate are enough as to repel further entrance of electrons from the anode of the battery. This force is represented in this frame by the magenta arrows on the yellow lines. On the upper plate, a similar situation occurs. When the accumulation of positive charges are enough to repel other positive charges, no further positive charges will enter. It is important to stress that the cessation of positive and negative charges flow will occur at the same time. This time will be when the voltage of the battery is matched by the voltage of the capacitor. So the answer to this question is true. Next question. Which capacitor has a higher reactance? A, 1 with 20 farads, B, 1 with 20 microfarads, C, 1 with 1 farad, D, 1 with 100 farads. The larger the area of the plates, the more the capacitance a capacitor has. That is, the more ability to store energy for a given voltage. So the smaller the capacitor, the larger the capacitance reactance. So the answer to this question is B. Next question. A capacitor will oppose high frequency current flow more than low frequency current flow. A, true, B, false. In this frame, I am representing two capacitors of equal value. Like all capacitors, they react to changing voltage and are oblivious to steady voltage. The capacitor on your left will see many bursts of voltage changes, thus will allow more total voltage to go through. The capacitor on your right will see fewer bursts of voltage changes, thus will allow less total voltage to go through. If we extrapolate this to one capacitor, the given capacitor will allow the fast activity to go through and not the low activity to go through. This is the basis for EEG filtering. So the answer to this question is false. A capacitor lets fast frequency go through while preventing the low frequencies from going through. Next question. Capacitors delay the voltage pulse introduced in a circuit, thus smoothing out a tracing. A, true, B, false. This frame introduces an open circuit at the time we will label T1. Now I am introducing a voltmeter in magenta color. This voltmeter is measuring the volts across the resistor. And another voltmeter in yellow measuring the volts across the capacitor. As you can see, they indicate zero voltage because the circuit is open. If we were to draw a line reflecting the value of each voltmeter, we will see two straight lines representing no voltage. So at time 2, the circuit is closed and the value at the voltmeters placed across the resistor will reach its maximum almost immediately, while the value of the voltmeter placed across the capacitor is not quite there yet. The numbers of the voltmeters reflects these findings. We can appreciate the difference in voltage produced by closing the circuit by looking at the line chart below corresponding to T2. As you can see, while the voltage across the resistor has abruptly increased and is now at its maximum, the voltage across the capacitor has increased gradually and at this time has not achieved its maximum. Now the time has passed and this is represented by T3. In this instant, the circuit is again open. The voltage across the resistor will drop precipitously, whereas the voltage across the capacitor will drop gradually. We can further appreciate this at T4, that is at time 4, at time 5, and at time 6. This attribute, that is the attribute to smooth changes in voltage, is used coupled with diodes to transform alternating current into direct current. So the answer to this question is true. Next question. Current flows through a capacitor during charging and discharging. True or false? When a capacitor is not exposed to voltage change, either because it is not exposed to current or because it is full, no current will go through. Current will only flow when charging and discharging a capacitor. So the answer to this question is A, true. Next question. Time constant represents the time it takes for a wave to rise or drop by blank percent. A 31, B 42, C 63, D 90. Time constant is usually expressed by the letter tau. Time constant indicates the time it takes for a capacitor to charge 63% or discharge 63%. The reason 63% was chosen has to do with calculus. The formula was arrived by executing a mathematical operation that consists of 1 minus 1 divided by a constant. The constant is 2.718. This number was chosen because it is the base of natural logarithm and was selected as the base of natural logarithm because the number hardly changes despite the exponential increase in regular numbers. So, executing the division aspect of the operation, we get 0.3679. That, when subtracted from 1, yields 0.6321, which has been rounded to 63%. So the answer to this question is C. Next question. In EEG lingo, the time it takes for voltage to drop to 36.8% of its maximum value is called the time constant. A, true, be false. In EEG lingo, the time for a wave to drop to 37% is called the time constant. The time constant of the wave represented in this frame is 1.5 seconds. So the answer to this question is A, true. Next question. When using a direct current, how long does it take for a capacitor to stop charging? A, 5 time constants, B, 3 time constants, C, 1 time constant, D, 10 times constants. I will answer this question by providing an analogy. This figure indicates the time it takes for a capacitor to charge. At this point, the capacitor has no charge. This figure represents the rectangle plate of a capacitor being empty. At this point, the capacitor has increased by 1 time constant. In 1.5 seconds, the time consistent with the time constant, the plate will get charged to 63%. So at this junction, the capacitor will be 63% full and 37% empty. During the next 1.5 seconds, corresponding to from the position of the arrow to the new position of the arrow, 63% of the available space that was previously empty will get full. So this constitutes that now the full space is 86%, leaving 14% of free space. During the next 1.5 seconds, corresponding to from the position of the arrow at this point to the position of the arrow that we just have presented, 63% of the available space will get filled. This will correspond to the capacitor plate being full to 94% capacity, leaving only 6% free. Next batch of electrons come again in 1.5 seconds, representing 1 time constant with a value of 63%. But remember that this is 63% of the free amount that was not filled previously. This will fill the capacitor to 98% and leave 2% empty. Next batch of electrons that arrive in the 5th time constant will fill 63% of the space that was not filled before, thus by now filling the capacitor to 100%. Thus taking 5 time constant or 7.5 seconds for the capacitor to get almost fully charged. So the answer to this question is A, 5 time constant. Next question. A capacitor that is charging and discharging all the time will allow more current to flow than one that is charging and discharging only some of the time. A, true, B, false. This frame represents a capacitor that, due to the frequency of the alternating current and the capacitance of the capacitor, is never fully charged or discharged. thus allowing current to flow all the time. In the lower segment of this frame, I am introducing a totally different situation. Here, the frequency is low and the capacitor proportion is small enough to become fully charged during the alternating current. As we previously mentioned, when fully charged, no current goes through. So the answer to this question is true. Next question. The total capacitance increases when A. Capacitors are in series, B. Capacitors are in parallel, C. Both, D. Neither. Capacitors in series decrease their capacitance. Capacitors in parallel increase their capacitance. I hope you recall from our last talk about resistor circuit this frame. It highlights the different behavior in regard to electromotive force, current, and resistance that rules the behavior of resistor circuits. I like to emphasize that the resistance of circuits made of resistors in series add up, whereas the resistance of circuits in parallel decreases as the number of resistors increase. Well, the reason I show you this frame is because the behavior of a capacitor regarding capacitance is different. When the capacitors are added in series, the amount of capacitance of the circuit decreases. When they are placed in parallel, the capacitance of the circuit adds up. So the answer to this question is B. They increase when in parallel. Next question. A 1.5 volt battery, when coupled with a capacitor circuit, can be made to yield 4.5 volts. A true, B false. This frame represents a parallel capacitor circuit on top and a single resistor circuit on the bottom. In this frame, the parallel capacitor circuit on the top is open, so the capacitors are not exposed to current. In this frame, the parallel capacitor circuit is closed, so the capacitors are exposed to current and become charged. As you know, based on Kirchhoff's voltage law, all capacitors are exposed to the same voltage, that is, the voltage of the battery. So, in a relatively short period of time, all capacitors develop a charge difference that is similar to the voltage in the battery. In this frame, the parallel capacitor circuit switch is made to contact the resistor circuit. At this point, the voltage stored in all the capacitors discharge becoming zero in a short amount of time and delivering 4.5 volts to the resistor. So the answer to this question is A. Next question. Capacitance voltage lags current by 90 degrees. A true, B false. In this diagram, the yellow sine wave represents current starting at the point indicated by the white arrow. The green sine wave represents voltage as a function of resistance. Current and voltage as a function of resistance are in phase. The aqua sine wave represents voltage as a function of capacitance. Voltage lags current by about 90 degrees in this situation. The magenta sine wave represents voltage as a function of induction. Voltage leads current by 90 degrees as a function of induction. So the answer to this question is true. In conclusion, capacitors are an important component of the EEG machine. Their most important function relates to their ability to separate electrical activity based on frequency, thus contributing to the construction of EEG filters. In addition, the capacitance of biological tissue contributes to the electrical profile of the biological signals. Thank you.